General-purpose robots must be able to perform a wide range of behaviors. While reinforcement learning can automate the process of acquiring these behaviors, learning them one at a time can be very slow. In this work, we study how multitask learning methods can amortize the cost of learning many skills, enabling new tasks to be built out of data collected for previous ones, and speeding up acquisition of new behaviors. To this end, we present MTOPT, Continuous Multitask Robotic Reinforcement Learning at Scale. MTOPT has three primary components: task definition, results in trained CNN success detectors; data collection, to generate episodes; and data sharing and distributed RL training to produce RL policies. Here we show several terminal images of a robot successfully grasping a carrot, as well as some failures. In this work, the task outcome is a function of the final image of the workspace. With this task definition, we can take the terminal image of an episode along with a task ID and query our CNN success detector to determine the episode outcome. Predictions from the CNN are used both as a sparse reward during data collection and to influence what off-policy data is used to train an RL policy. To collect images to train our success detector CNN on a new task, a non-technical user captures pairs of videos: a success video where each image frame can be used as an example of task success, and a failure video where each frame captures a task failure outcome. These images, along with relabeled pre-existing images from robot data collection, are used to train the CNN-based success detector model. Once this success detector is trained, we can use it during data collection. In order to collect robot data, we create a setup where the environment can be automatically reset. This allows us to collect training data across 6 robots with only occasional human intervention. We start with a lift anything and place anywhere task. Once we are proficient at the lift anything task and place anywhere task, we can learn more complex tasks with 2 strategies. We can relabel existing task data for more challenging tasks, and we can use the lift any policy to accomplish visually novel tasks. We have collected over 800,000 episodes, allowing us to learn about 14 distinct tasks with a single shared multitask policy. The policy proficient at these 14 initial tasks provides decent baseline performance on many novel tasks, which we challenge the robots with. We can then formally define and train policies for these novel tasks quickly. We've devised a large-scale distributed multitask reinforcement learning-based training setup to leverage this large, diverse data set. To leverage prior task experience efficiently during multitask RL policy training, we use a task data impersonation process. Task impersonation works by pooling useful success and failure episodes from relevant tasks. With our best impersonation function, the expanded data includes episodes from other tasks in the same skill, as well as from any other episode which succeeds at the current task. The per task expanded data is then rebalanced respecting task success. Our best data management pipeline significantly outperforms baselines, including those where no data sharing across tasks occurs, and in contrast, when all tasks share data with all other tasks. Our improvements are especially salient on tasks with small amounts of data, where we show up to 10x improvement over baselines. We continuously run data collection. The produced episodes are used both to incrementally define and add new task definitions, as well as train better policies. The whole process is highly iterative, with overall performance across all of the tasks improving over time. Even well-performing policies fail on occasion, dropping objects, missing the fixture, and sometimes just don't know what to do. Importantly, these episodes are efficiently utilized for continual policy improvement through our iterative multitask RL training. Thanks to multitask RL, our system exhibits emergent behaviors, like searching when the carrot is crowded by other objects, or repositioning when the carrot is trapped in the corner. Thanks to the closed-loop control policy, the robot will retry failed grasps and even chase the carrot or bowl when adversarially pulled by an experimenter. This is an example of generalization of the MTOP lift anything policy to a novel variant of the scene with objects in background that don't exist anywhere in our offline dataset. The system can also work with deformable and semi-transparent objects as demonstrated in this cloth covering task. Please see our paper for additional details. Thank you.